Alright, hello class. In this video we're going to be talking about the derivative as a function. And we've done basically the heavy lifting for this. In fact, we've already kind of seen how this works in the last video. But there are a couple of intricacies to talk about to sort of wrap it all up. But essentially all this is taking the derivative at each point, right, at each x value or t value or what have you, and creating a new function from the derivative at each point. Alright, so given the function f of x, the derivative function, which we will often call f prime of x, sometimes we will call it d by dx of f of x, but for simplicity's sake, we often just use f prime of x. Okay, and this is basically just a new function, right? Defined as, well, it's really just our, say, limit as h goes to 0 of f of x plus h minus f of x all over h, and this is for all x where the limit exists. Okay, so that's one thing here, is since the derivative is defined as a limit, it's not always going to exist because limits don't always exist, and we'll talk about that in a bit more detail in a little bit. But first, what we're essentially doing is, one, it's this idea here with the limit, right? We're just creating a new function with this limit, but you can also think of it in terms of the graph. So if we have, say, the graph of f of x, right? At each x, we can get, say, tangent lines, right? And each one of these tangent lines has a slope. Okay, so what we're essentially doing is creating a new function where if this is, let me label these as, say, x1, x2, x3, x4, what we're essentially doing is creating this new function by, at each x value, just assigning it to be the slope of the tangent line at that point. Okay, so f prime of x2 we would just set to be m2, the slope of the tangent line, which we get using, of course, this limit here. Okay, I have a better graph we can take a look at. Okay, but this is basically the overall idea, that we are creating a new function from the derivative at each point where that limit exists. Okay, so here we have a graph. Let's say this in blue is our f of x. Okay, and I already have a tangent line here, and if I move it back here, so notice at this point I have the slope written up for m. Okay, so here the slope is 17, so the instantaneous rate of change of this function at this point is 17. So as we move it along, we'll see that the slope is still positive, but is decreasing, right? So this function is still increasing, however, the rate at which it's doing it is going down. And then around here, we're going to hit like a 0, and then it's going to start decreasing. And when the function is decreasing, we start getting negative slopes. Okay, and then again it starts to increase again, and we're back up to having positive slopes. Okay, now at each of these, if I create a new function from the same x values but making our y values the slope, okay, we'll get these points here. So these points in orange here are basically aligning, and we're actually off the graph here, so let me zoom out so we can see it all the way up here at 17. Okay, and there we go, there's a better window. So here at x equals -2, we're creating the point -217 because that aligns with the slope of the tangent line there. And at each point going forward, that's what we're doing. We're keeping the same x value, but then making a new y value, okay, aligning it with the slope. Okay, now if we chart that out with a curve, okay, we'll see that we have the graph of a new function. Okay, so when the original function is increasing, notice that the derivative function is positive but decreasing, because what is happening, oh, look at that, I didn't realize I could do that. The derivative is positive but decreasing because the original function is increasing, so it has a positive slope. However, its rate of increase is going down. Then eventually, right, it hits 0 when the function itself changes from increasing to decreasing, and then we're getting negative values. Okay, and then eventually, right, negative, and then we're back up to increasing again, and when that happens, the derivative is positive again. Okay, in fact, this path is charting along this function here. Okay, so that's essentially what we're doing when we're creating this new function. This new function gives us a lot of information. It tells us when the original function f is increasing or decreasing and when it turns around. All right, so to sort of summarize some of this, given a function f of x, wherever f of x is increasing, that corresponds to where f prime is going to be positive. Wherever f of x is decreasing, that corresponds with where f prime is negative. And wherever f turns around, right, we're going to get that f prime is either 0 or undefined. And I'm going to explain that in a little more detail later. But basically, if it's a smooth turnaround, you're going to get f prime is 0. Okay? If you have a sharp turnaround, that's when you're going to have something like f prime being undefined. But from here, we can actually sketch graphs of f prime given f. All right? So, well, how do we do this? How would we go about sketching a quick graph of f prime if we're given f? Well, if this is f, right, wherever f is increasing, okay, f prime needs to be positive. All right, so here f is increasing and then stops. Okay, so let me use a different color here to break this down. Then f decreases all the way to here, stops and turns around to be increasing again. Okay. And then once again it increases to this point, stops, increasing, turns around to be decreasing again. Okay, and then decreases. So we're going from increasing to decreasing to increasing to decreasing. Okay, so in this region that I just made, okay, f is increasing. In this region, this second region, f is decreasing. in this region, f is increasing again, and here f is decreasing. Okay? So, wherever f is increasing, f prime needs to be positive. Where f is decreasing, f prime needs to be negative. Increasing, f prime is positive. Decreasing, f prime is negative. Okay, so in this region here, f prime needs to be positive, so it needs to live up here, right? So it will live up here. Okay, then it jumps down to being negative, so then the function will live here, then back up to positive, and then negative again. So, at these points, right, where this swaps, right, f prime is either going to be 0 or it has a jump. In this case, it's going to be 0. So, provided f prime is continuous, we'll get into that in just a second. Okay, but our function for f prime, okay, is going to be something like this now. It needs to be positive, and we know it should be decreasing because these tangent lines, right, you can see that the slopes of them, right, the steepness of the graph itself is going down. So that tells us that f prime is decreasing. Then we're going to get something like this, and then something like this. Okay? So, what we're essentially doing is just connecting the dots with a nice continuous curve. Okay? And just remember, wherever f is increasing, f prime needs to be positive. Wherever f is decreasing, f prime needs to be negative. So on, so forth. Okay, so now I think I've put it off long enough to talk about what happens when the function or the derivative does not exist, right? When it's undefined. So that's what's called differentiability. So we say a function, okay, is differentiable at a point, let's say x equals a, when f prime of a exists. So remember, f prime is a limit, and limits don't always exist. Therefore, the derivative is not always going to exist. Okay, so to talk about what's happening when a function is not differentiable, let's look at the function, the absolute value of x. Okay, so remember, the absolute value of x is equal to x when x is greater than or equal to 0, and it spits out a negative x when x is negative, right? If the x is positive, we don't do anything. If x is negative, we renegate it to make it positive again. Okay, so the question is, well, we have a few. What is the derivative with respect to x of the absolute value? So here's where this notation comes in handy, because you can just throw this d over dx here to say the derivative of this thing. Okay, so I don't have to like call it f of x, for example. So what's the derivative of the absolute value of x? Does it exist everywhere? Okay. So I kind of went off the range there. All right, so what I want to look at here is that limit, right? So specifically, does the derivative with respect to x of the absolute value of x exist at x equals 0? Okay, that's the point I want to look at. All right, so let's see. I think I will call this f of x just to simplify things. So does f prime of 0 exist? All right, so f prime of 0 is going to be the limit as h goes to 0. And using our definition, I'm going to use the difference quotient one. It will be the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. Okay, so this will be the limit as h goes to 0 of, this will be the absolute value of 0 plus h minus the absolute value of 0 all over h. Okay, so we end up with here the limit as h goes to 0 of the absolute value of h over h. So, to analyze this, we've seen this before, right? When it comes to calculating limits, what we do is look at either side, because with the absolute value, we're going to get something different on each side of 0, right? So the limit as h goes to 0 from the positive side of the absolute value of h over h, well, since we're on the positive side, this is h greater than 0, right? So we're going to get that just normal h over h, which is 1. Okay. However, the limit as h goes to 0 from the left of absolute value of h over h, here our h is negative. So we're going to negate that absolute value of h to get negative h over h, which is negative 1. All right, so from the right and the left, these do not match. Okay, so this limit does not exist. Okay, well, what's happening here? Well, it turns out if we take a look or remember what the absolute value of x looks like, it makes a V shape. Right, so here is the graph of the absolute value of x, and what we can see here is it makes a V shape and has a sharp turn here. In fact, this is made up of two lines. This is the line negative x, and then suddenly it jumps up to be the line positive x. Now, if you calculate the derivative of negative x, you get negative 1, and if you calculate the derivative of just x, you get 1. That's the rate of change of those, and since they are linear functions, they have a constant rate of change, which is their slope. And if you take a look at the, say at any given point, the tangent line, well, you'll notice the tangent line just lines up with the line itself. You'll always see that with linear functions. However, as we move along, let me not show that yet, as we move along, it just jumps, okay? And then here at 0, notice we don't have a tangent line because we don't have a slope there. But what's happening is, here we go. The slope is negative 1, and then suddenly it jumps to 1. So if we trace out, like we did before, okay, a derivative function, when x is in the negative values, we get negative 1, and then suddenly it just jumps up to being positive 1. Okay, so let me get rid of that for a second. And all right, so as you can see, as we trace along this graph, we get a jump there because on one side of the function the derivative is always going to be -1, and then suddenly on the next side or on the other side it's suddenly +1, so we have a jump. Anytime we have a sharp turn like this, we're either going to have a jump or say some sort of asymptotic behavior. Alright, so essentially if a function has any sharp turns, then it is not differentiable there. So any sharp turn, any cusp, any spikes, this is where the function is not differentiable. Further, if the function itself, if the original function is not continuous at a point, it's not going to be differentiable either. Okay, further, if f of a is not defined at a point, it is not differentiable there either. So basically it's because if you say have a graph and like you have a hole there, when you go to find the derivative, right? So if you're trying to find f prime of 5, when you try to find the limit of f of 5 plus h, well, you can find values here, but f of 5 itself is undefined. So that's going to make this whole thing undefined. Right, so that means that if you have a blow-up point, right, so if you've got, say, blow-up, f prime is also going to blow up. Okay, and if you think about why, well, if you look at the tangent lines, they start getting higher and higher on both sides. So the slopes themselves, okay, are going to start increasing to infinity as well. Okay. All right, so here's an example where, or another example with a little cusp, right? We have a sharp turn here. And if we start looking at the tangent lines here, we see that, let me not show that yet, we see that they get larger and larger and larger and larger, and then they are going to sort of jump suddenly to being decreasing. Okay, to show what I mean, as we get closer and closer to 3 here, the slopes are getting steeper, larger and larger and larger. They're positive, and then suddenly, bam, they are negative. Right? So if we actually try and chart this out, we'll see that we get this jump, and then, right, we're going up to positive infinity, and suddenly we're down in the really steep negatives. And so what's happening here is at cusps like this, it's either going to be, well, I mean, it's always going to be a jump with a sharp turn. But in this case, the tangent lines are getting larger and larger, so we have a blow-up. So we don't need a blow-up in our original function to get blow-up in the derivative. Okay, and we can see it in cases here. And the original function could still be continuous and yet still not have a derivative. So being differentiable is a much stronger condition than just being continuous. All right, and really, any place that is going to cause a vertical tangent line is going to be a place where the function is not differentiable. Okay, so for example, this one here, you see that we have a moment where the function itself looks vertical. Well, if we look at the tangent lines as we go forward, as we get closer and closer to 0, the function gets steeper and steeper and steeper. Okay, and here, really close to 0, we see that we have something very, very almost vertical. And then it's going to jump. Okay, so what this is getting closer and closer to is this vertical line here. Okay, this is the tangent line of the function at this point. It's a vertical line, therefore it's an undefined slope. So essentially, anywhere that's going to cause a vertical tangent line is also going to cause a function to not be differentiable. Okay, so just to round that up, any sharp turns or points that cause a vertical tangent line is where, or are where, is where f prime does not exist. Okay, now, given all of this, if a function is differentiable on, say, an interval, we say that that function is smooth. Okay, and the reason we do that is because, well, this right here would be differentiable. It's smooth, right? It literally is smooth. So this is smooth. So f prime exists wherever we want it to here. Whereas this function is not smooth. Right? Because here we have places where f prime does not exist. All right, with the time we have left, let's do some more complicated derivative calculations. In the last video, we did some with, x squared, x cubed, that sort of thing. Let's look at one that, say, uses a square root. So let's say f of x is equal to the square root of x. We want to find f prime of x. Well, to do that, remember f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so we will replace the f of x plus h with the square root of x plus h, and we'll replace the f of x with, well, f of x, which is just the square root of x. Okay, and now we are going to be calculating this limit. So remember, this is where we go back to all of the limit techniques that we learned previously, and so we're going to use a conjugating factor here. Okay, so we will just change that middle term from a minus to a plus and multiply the top and the bottom by this. Okay, so when we do that, remember the beautiful thing about this is this becomes a difference of squares. So this will be the square root of x plus h all squared minus the square root of x squared. And then I'm not going to mess with the bottom. I'm going to leave the bottom the way it is. Okay, and it will be h times the square root of x plus h plus the square root of x. So the beautiful thing here is that those square roots disappear. So we get x plus h minus x on the top. And remember that the bottom does not change. Okay. Now, here the x's cancel, so we're left with h over h times this square root stuff that we are not messing with. And as always, the h's cancel. Okay, that always happens. And so we are left with now the limit as h goes to 0 of 1 over x plus h square root plus the square root of x, and h is going to 0. So we're left with 1 over the square root of x plus the square root of x. So this comes out to be 1 over, well, we have 2 square root x's there, so it's 2 root x. Okay, so if f of x is equal to the square root of x, f prime of x we just found is 1 over 2 square root of x. Wonderful. All right, let's do one that's a little more complicated now that we have, this fraction thing. Let's say f of x is 2 over 5x plus 3, and we want to find the derivative function, right? So remember that's going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And this one's going to be a pretty funky one because we're going to have a fraction within a fraction, but again, we're just going to employ the same tricks we used to do with just the limits in the previous module. Okay, so f of x plus h, all we're going to do is replace the x with x plus h. So we're going to get 2 over 5 times x plus h plus 3. Okay, then we'll have minus 2 over 5x plus 3 because that's just our f of x. Okay, and then this whole thing is going to be over h. Now, my preferred way of doing fractions within fractions is multiplying the top and the bottom by the denominators that we have. Okay, so before I do that though, I would like to simplify this denominator since 5 times x plus h plus 3 is going to be 5x plus 5h plus 3. I just want to simplify it that way. Okay, so let's go ahead and distribute that. Okay, so now we're going to multiply the top and the bottom by these two denominators multiplied together. Okay, so the 5x plus 5h plus 3 times the 5x plus 3. Multiply both the bottom and the top by it. And doing that, when we distribute this across, okay, here the 5x plus 3's will cancel and we'll be left with just this, and here the 5x plus 5h plus 3 will cancel and we'll be left with just the 5x plus 3. Okay, so here I'll have 2, and the larger denominators cancel and we're left with just the 5x plus 3. Okay, the minus sign sticks around, we'll have the 2, and here the smaller denominators cancel and then we're left with the 5x plus 5h plus 3. Okay, and this is all over h times these. We're going to leave that denominator alone. Okay, now we're just going to simplify the top. We'll distribute that 2 across, and then we should get a lot of things canceling when we do that. Be real careful. You're going to bring that negative 2 in. That's one mistake I see a lot. Okay, so this will be 10x plus 6. If you don't bring that negative 2 through, you're not going to get all the cancellations that you want. Right, so we're going to get a negative 10x minus 10h minus 6. So that cancels out the 10x and the 6. Okay, and then in the denominator, well, we're not going to change it. Okay, not going to change it, and now I've just rewritten it with all this stuff gone, and now the h's cancel. And we should be able to plug in the h directly now. Right, and thankfully, remember we're taking the limit always with these as h goes to 0. Right, so that's going to go to 0, and we'll just be left with negative 10 over 5x plus 3 times 5x plus 3. Oh, well, that's just negative 10 over 5x plus 3 all squared. And there we go. That is going to be our derivative function. Okay, so if f of x is 2 over 5x plus 3, then f prime of x is negative 10 over 5x plus 3 squared. Okay, I mentioned in the last video about Pascal's triangle and how it can really speed things along for you. To show how it does that, if you've never seen Pascal's triangle before, you start with a 1, 1, 1. Then you do 1, 2, 1, because what you do is you always start with a 1, and then the next piece is the previous two sort of adjacent, diagonal, however you want to call it, added together. Right? So you go 1, 1, 1, 1, 2, 1, and then it will be 1, 3, 3, 1. Right? Because of the 1 and the 2, the 1 and the 2, then you'll have 1, 4, 6, 4, 1, then 1, 5, 10, 10, 5, 1. Right? You're always adding to get the next pieces. Now, what does this do for us? Well, in terms of raising, let's say, what we'll be using is x plus h to certain powers, this gives us the coefficients because, say, x plus h to the 0 is just going to be 1. X plus h to the 1 is just going to be x plus h. And here's where we're going to start seeing it. X plus h squared is going to be x squared plus 2xh plus h squared. Notice that the coefficients here, 1, 2, 1, line up with these numbers here. Same here, we have 1 and 1. Okay. For x plus h cubed, we're going to get x cubed plus 3x squared h plus 3xh squared plus h squared. Notice the coefficients here, 1, 3, 3, 1. Sorry, did that wrong. H cubed. Okay? So notice what's happening here. The coefficients match what we get on Pascal's triangle, and then we go from x cubed, x squared, x, no x, then h cubed, h squared, h, no h. So the x's decrease in power while the h's increase in power. Okay, so then x plus h to the 4th, that's going to be x cubed plus 4, sorry I keep doing that, x to the 4th plus 4x cubed h plus 6h squared, x squared h squared plus 4x h cubed plus h to the 4th. All right, so once again, the coefficients line up exactly with what we got in Pascal's triangle, and the powers follow that same pattern. We start with the 4th and reduce down with our x's, start with h to the 0 and move up with our h's. All right, so that gives us a really quick way to do these derivatives. So if you ever see like your math teacher or somebody else do these expansions really, really quickly, it's not like that they're a genius, right? It's not that they just have them all memorized. What they're doing in their head is this Pascal's triangle. Okay, so from here, if we wanted to find the derivative of x to the 5th, right, we have a much quicker way to do it now, because when we go to find f of x plus h, well, f of x plus h is going to be x plus h to the 5th minus x to the 5th over h. Okay, and this, well, thanks to Pascal's triangle, we don't have to expand it out step by step. We just know that this is going to be x to the 5th plus 5x to the 4th h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the 4th plus h to the 5th. Then we have minus x to the 5th. Okay, so like always, the non-h terms all cancel, and then we can, in the next step, factor out an h, and I'll do that quickly here by just saying h cancels with this h, one of these h's, one of these h's, one of these h's, and one of these h's. Okay, so we end up with 5x to the 4th plus 10 x cubed h plus 10 x squared h squared plus 5x h cubed plus h to the 4th. Okay, still quite a bit of work, but all our h's are going to go to 0. And so what we have is that the derivative of x to the 5th is 5x to the 4th. Now, for those of you who have taken calculus before, or seen this stuff before, you already knew that, right? There is a pattern that we can employ that simplifies this process. And so that's what we're going to be looking at in the next lesson is how do we simplify this so that we don't have to continue doing this limit thing over and over and over and over again. Okay, so with that, I'll go ahead and bring this one to a close and look forward to the next video where we, thankfully, have a much better way of finding derivatives without having to crank through the limit. However, there are certainly places where that limit is going to help us. Okay, so I'll catch you on the next one. Cheers.